So for 4.6 for dimension, so we talked about how we were determining if things were a basis for a coordinate system. And so if you have a finite dimensional vector space, so that's what we've been dealing with. We haven't been dealing with infinite vector spaces. We've been dealing with finite dimensional vector spaces. And so you might find different bases for that vector space that you're looking at. But what they want you to know from theorem 4.6.1 is that all of the bases that you might define, they will have the same number of vectors. And so here they have also this theorem 4.6.2. They say let V be a finite dimensional vector space. Okay, we're used to that. And then here they're saying V1 all the way through Vn. Let's let that be any basis for V. It says here, if a set in V has more than those n vectors in the basis, then it is linearly dependent. So that means if it's got more than that basis, that means like some of those vectors in there are going to be linearly dependent. And then it's also saying on the other hand, so if it has more, it means some of those vectors in there in the basis are going to be linearly dependent. And then it's on the other hand saying that if it has fewer than n vectors, then it's not going to span V. So it's not going to be a basis there. So we've got some different theorems there going on. And so they say that here we have the dimension of a finite dimensional space vector V is denoted by dim V. So that's how we're going to denote dimension. And all it is going to be the numbers of vectors in the basis for V. And then the other thing that they want you to note is that the vector, a zero vector space has a dimension 0. So zero vector space, dimension is 0. But here your dimension is just going to be the number of vectors in your basis. So go ahead and keep that in mind for your one of your important definitions. And then we're going to be looking at some other stuff here. So let's go ahead. The other cool thing too is they mentioned later on is that you might have a set S that might span V, but it might not be a basis yet. It could be possibly reduced to a basis by removing vectors, like if it had too many and some of them were linearly dependent. So if you removed some, you could actually reduce it to a basis. And then it says here, if S is a linearly independent set that is not already a basis for V, you could actually enlarge it by adding in another appropriate vector such that it would be a basis. So those are things to keep in mind as well. All right, so let's look at our problem here. We're going to go down to what you guys need to do. So for our section 4.6, they are asking us through exercises 1 through 6, find a basis for the solution space of the homogeneous linear system and find the dimension of that space. So they're telling us, okay, you got to find this basis and then you got to tell me what the dimension is. Problem 2. Okay, so what is it asking? It's saying, okay, we got to find a basis for, okay, so we got to find basis. And in particular, it's of a homogeneous linear system. And they also just want to say, they say find the dimension. And so this, we know from our definition, that's going to be the number of vectors, right? And it's going to be abbreviated dim V. Okay, so with problem 2, here we have our equations here. So we got 3x1 plus x2 plus x3 plus x4 equals 0. And then we got 5x1 minus x2 plus x3. Oops. And I think we have minus x4 equals 0. Yeah. So the first thing you're going to want to do with this is you're going to probably want to solve this, right? To actually find the vectors that are going to form the basis, right? So how would we go about solving this? What might be a good way of solving this linear system? Thinking back to previous sections. Yeah, I like it. So a really good way to do it would be like what you just said, would be to form an augmented matrix. So here we'd have this augmented matrix of 3, 5, 1, -1, 1, 1, 1, -1. And what would be the last column? We're doing an augmented matrix. Yeah, we got zeros. So what would you want to go ahead and do with this? What techniques? We got to reach deep back. What are we doing with this? Well, hopefully you'd want to start working with it and do your different operations, and you'd probably want to get it down to your row echelon form here. So what would be one of the first things we could do here would be to divide our first row by 3, right? So we'd have 1, 1/3, 1/3, 1/3, and 0. So here we divide by 3. This one here, you'd have this. So that'll be the first step. Here, then, what might be your next step? If you're trying to reduce this. Well, you might multiply the top row by -5 and add it to the second row, right? So -5x first row added to second. So then here you would have 1, 1/3, 1/3, 1/3, 0. Ooh, here's where the math. Okay, so if you have -5 times 1 plus 5, that would give you a 0. Here's where you're going to have to get into some algebra here. So here you'd have -5/3 minus 1. Anybody want to take a guess at what that'd be? Oh, good job. Yeah, it'd be -8/3. Then the next one over would be what? -5/3 plus 1. What would that be? Oh, good job. Then we've got the next one, -5/3 minus 1. So we got another -8/3 here again. And then we got zeros and zeros on that one. Okay. Then another easy step here. What do you want to do to get rid of all those fractions? Help yourself out. You probably go ahead and you multiply the second row by 3, right? So you have 0, -8, -2, -8, 0. Ooh, now what would we do? Oops, sorry. This one is a 1. Now what are we looking at? Probably going to divide by what? Yeah, divide by -8, that second row. So we got 1, 1/3, 1/3, 1/3, 0. Then we got 0. So -8 divided by -8 is 1. -2 divided by -8 would be 1/4. Then we got -8 divided by -8 would be 1. And then we've got a 0 here. Ooh, now what do we want to do? Anybody have any ideas here? Well, we do one more step and we'd put that in more, even further reduced form. So hopefully you should get something like this as your final things to work with here. So what do we do with this? What can we say about this? So how would we put this into, well, if this is our x1 value, here's our x2, our x3, here's our x4. So what do we got? We've got x1 plus 1/4 x3 equals 0, right? And then we can go from there and say that x1 equals negative 1/4 x3, right? We have from our second one, what do we got there? We've got x2 plus 1/4 x3 plus x4 equals 0. So from there, you could say that x2 equals negative 1/4 x3 minus an x4, right? We rewrite that. So we really can't say too much about anything else. So we would want to assign x3 arbitrarily to s. We're going to have to put this in our parametric equation format. And we're going to say our x4, we'll assign that to the parameter t. And then how would we rewrite everything? Then x1 is going to equal negative 1/4 s. And then we've got x2 is going to equal negative 1/4 s minus t. So here's going to be our parametric equations for this solution here. So how would we write that? Ooh, boy. How would we write this in vector form as a basis? Oh my goodness. So here we want to get it in our form here of x1, x2, x3, x4. If we're going to put this kind of in our vector coordinate form, you could write this like here using our parameters here. We got negative 1/4 s. We've got negative 1/4 s minus t. We've got s and we've got a t. Now, one thing you should notice from previous sections is we would want to pull out those s and t's. So how would we rewrite this? Here we'd want to pull out our s's and t's. So if we had s times all these coordinates, what would that look like? So for the first coordinate, if we pulled out the s, what would we be left with? Yeah, we got negative 1/4. Then we look at that second coordinate, pulled out the s, still have 1/4. Is there an s term in that third coordinate? Yes, there is. There's a 1. For the fourth coordinate, is there any s term? No, so that would be a 0 here. And then we're going to pull out our t. And so for that first term, there's no t term, so that'd be a 0. Here, oh, we have a negative t, so this will be a negative 1. For that third term, we have no t's, and for that last one, we have a 1. So here are our two vectors that can form a basis for v. So here is a vector, and whoop. So this vector and this vector are a basis for v. And how many vectors are there? 2. So your dimension here is 2.